Thank you for inviting me near the Donau. I have to present two apologies. The first one is for speaking of analysis in a obviously very algebraic conference. So my excuse is that some algebraic results like computing Galois groups and solving inverse problem presently are most efficiently solved by analytic means. Maybe it can change. And the second apology is that since I wanted to give some, at least some information about some recent results, the end of the talk will be very technical. Hopefully, I will not have enough time to get to the end of the talk. so maybe you can avoid a lot of suffering. So the whole theory of difference equations has been deeply influenced by Marius van der Put and Michael Singer. And one of the influence here is that I will use Michael numbering starting from -16 and going until 0, so that you can see at every moment how much time is left for suffering. So I speak of a local analytic theory of complex linear Q-difference equations. The most analytic parts there are summation of divergent solutions, because as soon as there are irregular equations that will be more or less defined a bit later, there are divergent series that look a bit like the divergent series of differential equations, except that here factorials are replaced by other ways of growing. Then there are asymptotic theories, of course. And so these two things, summation and asymptotics, I will say very little about it. And then there is analytic classification and Galois theory. Galois theory means defining computing Galois groups and then solving inverse problem. So a lot of the work in these areas was done by Jean-Pierre Ramis, Shangyi Zhang, and myself in the last decade. But as I said, I will not speak of the first two areas, only the last time. And I will, the recent improvement I am speaking of is that the strongest result that we obtained with Ramis and Zhang were about with a technical assumption about the Newton polygon, that all slopes were integral. And so recently I am able to really relax this assumption. So for the general theory, I strongly encourage you to read the lecture note by van der Put and Singer. Then also for the formal theory, you can see the paper by van der Put and Reversa. So I say that to distinguish, I'm going to do the analytic theory here, which is less algebraic, of course. Okay, functional equations will have the following form. So we use what was the P class in the previous talk, f of qz as a basic functional morphism, and then we iterate it, and then we form only linear equation. So it's good to have a Fildarian, well, a thread to follow the kind of theory we are trying to build by thinking of differential equations. And one of the analogies, not the best one, but one which is enough for many purposes, is instead of f of qz, you think of f prime of z. Better analogy is z f prime of z. Other analogies are still better. But this one is already enough to see what kind of thing we are trying to do. So in local analytic theory, we have to solve, of course. And solve mean basic special functions. Here, theta functions replace the exponential. And then you have power series. And the power series may be divergent, and then you have to make a summation process, and then to prove asymptotic properties. Then in local analytic theory, you have classification, and this has historically two species. One, which is called here Stokes cocycles, or or Birkhoff-Malebranche-Cibouillat is actually the irregular version of Riemann-Hilbert correspondence. So you see, I called something Birkhoff-Malebranche-Cibouillat. Maybe some of you know the theorems of Malebranche-Cibouillat for differential equations, but Malebranche says that they originate in Birkhoff, so I call them that way. And then there is a second way to classify differential equation, is to use representation of algebraic groups, and this is what Galois theory does. So differential Galois theory say that you can associate to any differential equation a representation of some very big, actually pro-algebraic group, and Riemann-Hilbert correspondence say that you can associate to every differential equation a representation of the fundamental group. And so we are trying to do something similar here. As I said, the most analytic parts of this were studied mostly by Ramis and Zhang, and the most algebraic part were by Ramis and Zhang and myself. And so, as I said, I will only speak of the last two ones. Okay. So we take a complex number with modulus bigger than 1. We can take it between 0 and 1. It's symmetric theory. The formula changed slightly, but it's completely equivalent. But if you take modulus of Q equal 1, the theory becomes completely different. And in the analytic side, it is much more complicated. We have this operator of interest. The most important fields are K, which are the meromorphic germs at 0, and the hat over K, which are the formal germs. Okay, so for formal theory, hat over K, but for analytic theory, it is K. Today, I speak only of local theory at 0, not global theory. A Q difference equation looks like that, and using the operator sigma Q, we can write it in more compact form, where the coefficients A1, etc., AN are not 0 and are analytic. And of course, we can vectorialize it, and we have a Q difference system with a matrix and an invertible matrix, and it is equivalent. There is something equivalent to the cyclic vector lemma. If we want to solve, we don't have to solve. We can classify without solving, but if we do want to solve, we have to build enough solutions, and we have to go about the big field of meromorphic functions over all of C star. Actually, for local theory, I should have written C star, comma 0 to say that we take germs at 0, but most of the time we can boil down to this setting. Then if we have a field which is big enough for solution, we have some equivalent of the Wronskian lemma, which says that, we have some equivalent of the Cauchy theorem, which is that we have enough solutions that is n-dimensional. Wronskian lemma says that if you take an arbitrary field, you will have dimension at most n. And, but this is dimension over the field of constants. And the problem is that if we take a big field for solution, then the field of constants is big also. So we have here a field that is rather big. It's not the field of complex numbers, so it is some kind of problem because, as you know, for instance, Picard-Vissot theory insists that we don't get too many constants. So if we want to have complex numbers as basic invariant, this could be considered as a problem. However, it's not such a bad problem because the field of meromorphic functions above C star over Q to the Z is actually a field of elliptic functions. It's not such a big bad field. Okay, so the fact that you have enough solutions when you take this field, it's not done like in Cauchy theory. We don't have equivalent of Cauchy theorem here with the integrals and the explicit solving. The only proof I know is something that says more or less that a vector bundle over C star is holomorphically trivial. And the vector bundle over C star over QZ, which is a compact Riemann surface, is meromorphically trivial. Okay, so we obtained global solution, and from the beginning, one problem is that there is no kind of analytic continuation in this theory. All functions that we obtain are uniform. So the ambiguities that allow one to use the fundamental group and then more algebraically global group cannot be used here. You have to take an entirely different way. And also, since we have a big field, there is some work going down to C. For classification, we have to define equivalence of system. So the usual way is gauge transform. You say that you have a system with matrix A and another system with matrix B, and you say that you can go from one to the other if there is a matrix F that transforms solution of one into solutions of the other. And this is equivalent to the relation that is written at the middle, B equal this expression F applied to A. So this is the kind of gauge transformation we can do here. And if F is analytic, then you have analytic equivalence. If F is formal, you have formal equivalence. Then you are going to try to build invariants. The first one are formal. The first invariant is a Newton polygon. I will not define it. I will give just a hint of what it looks like. It has two vertical sides and a convex part at the bottom, and the slopes are ordered from left to right. So they are increasing, and this is very important. There is a dissymmetry in the theory, and each slope has a multiplicity, which is just the abscissa here. Okay, so this is the way slopes are defined from the drawing. And the proposition is that when it is defined, which I did not, the Newton polygon is a formal invariant. There are other invariants here, the exponents, similar to the exponents for differential equation. I will not need them. And there are formal invariants. Okay, so the second most important fact that appears in the theory is that analytically, every matrix can be put in a block triangular form according to the Newton polygon. I give at once the formal statement, which is that it can be put formally in block diagonal form. This statement is also true for differential equations. It's called breaking the Newton polygon. But the first statement has no equivalent for differential equations. It's something typical of Q-difference equation. So I will recall that any matrix has this form analytically, and formally it can be reduced to this form. So I consider, so the various blocks corresponds to the slopes, and each block corresponds to an equation having only one slope, so I call it pure isoclinic. And you can impose something about the coefficients that appear here, U upper right. Okay, so from now on, I suppose that all matrices are in this form. They can be reduced to this form, and this can be made compatible to every algebraic structure, for instance, to the tensor structure here, so that it doesn't spoil the Galois theory to assume that. And we consider that A0 is the formal reduction of the matrix A. So it encodes its formal class. And the analytic and formal classifications is the same if you consider only pure matrices with only one slopes. It's only when you have many slopes that it changes. And you know that for differential equations, the difference between analytic and formal classification is given essentially by Stokes operator, Stokes ambiguity. So the formal statement says that you have a unique formal gauge transform here, or a reduction, if you impose that f hat respects the filtration that you see here and the graduation that you see here. And so you see that here you have identity matrices with the proper sites, 0 here and something here, and this you consider as an algebraic group over any field included in GLN. So it will have some use in the following. So the f hat, which realizes this formal reduction, is of course a divergent object generally. It can be controlled. That is, you can say which kind of in which kind of way the series increase, the coefficients of the series increase. And of course, it should be submitted to summation theory, which I will not do here. We will go around this problem. So you know that classically summation theory says you have such an object which is divergent and which comes from an analytic differential equation, and you can associate to it in some way an object which is analytic, which is asymptotic to the first one, and which satisfies the same differential equation. And in which way are these summed objects, these summations, analytic? They are usually, in the case of differential equations, they are usually defined in sectors. And these sectors are encoded by intervals on the circle. And here, oh, I've gone a bit in advance, so this is what I will speak about in a minute, sorry. So I speak of classification in differential equation theory. Classification is on two sides. On one side, you have the equation, you do manipulations with the coefficients of the equations or the matrices or the system. On the other side, you have transcendental objects. And the Riemann-Hilbert correspondence says that you can go from one side to the other, but you must have two sides. So for instance, if you have the left side, you have the space of normal forms for the matrices describing differential equations. Here you have something like that. You can compute exactly the set of analytic classes within a formal class and show that it is an affine space and compute its dimension. So you have complete solution of this problem. The dimension that is computed here can be read off on the Newton polygon. It is just, sorry, the area of the finite part. Okay, when the slopes are integral, you can do something better because you can normalize in this way with AK matrix with constant coefficients. And then you have a very specific normal form and set of coordinates on your space. In the case of non-integral slopes, we do not have nice statements like this one. So there are more complicated statements like one in a paper by Virginie Bugeaud to appear in Annales of Fourier. Okay, now I am going to try to go from the left-hand side where we manipulate matrices and coefficients of equations to the right-hand side of the Riemann-Hilbert correspondence when we build transcendental objects and hope that they are classifying objects for the objects on the left-hand side. For instance, in classical Riemann correspondence, you start from a question, and you build some solutions, and then you keep only the monodromy data relevant to that solutions. These monodromy data can be interpreted after Hilbert as the representation of a group, and so you have a one-to-one correspondence between, on one side, classes of equations, and on the other side, representation of a group. But you have to have two sides. So what are the two sides here? That's Birkhoff, who systematized the look for transcendental side in the case of Q difference and difference equations. And in some sense, in the irregular case, this is provided by a generalization of Stokes operators. So I strongly encourage you not to read this proposition, which is fundamental. I said that this f hat in differential theory can be realized by various analytic functions over various sectors, and the ambiguities of these various analytic functions realizing the same divergent. These ambiguities are Stokes operators, and they are the invariant we are looking for. So what are we getting here? What we are getting is something different. Sectors are in C star, and they are replaced by the plane deprived of a discrete Q spiral. This is what replaces the sector here. And so a sector is encoded with AQZ, which is an element of C star over QZ, which is actually a complex torus. So you have the usual circle of differential equations is replaced by a complex torus, and the sectors are replaced by open sets of this form. And what I say is that I can realize this formal data by a matrix that is holomorphic over C star deprived of the spiral. And in differential case, you have control of how the solutions grow near the boundary. And here it is replaced by the fact that you have control about the poles and the multiplicity of the poles. So this is what says that that proposition here. And when you have defined it, this FC bar, which is the sum of f hat in direction C bar in EQ C star over QZ, it realizes the same properties as the first one, and in some sense it is asymptotic to f hat. Okay, so this is what a resummation will look like in our setting. So in differential case, you take many sectors, many resummations, and you take quotients of them, the ambiguities of summations, and call that Stokes phenomenon or Stokes operators. So you do the same here. And since FC bar goes from A0 to A, if you go and then you go back, you have something that goes from A0 to A0, and it depends on on C bar and D bar, two directions. And it is an automorphism of A0 in this group here. And so it belongs to a sheaf. So I go a bit swiftly here, don't look too much to the detail. For every C bar, D bar, you have an element of some sheaf. And so you have a cocycle for some covering. The sheaf is over this curve here, this complex torus. And the classical theorem of Malgrange-Sibouya, that is for differential equation of Birkhoff-Malgrange-Sibouya, say that this is exactly a classifying application. So the equivalent here theorem is about the big arrow from completely at left to completely at right. That is, it says that the set of equivalence classes, which is completely at left, is in a one-to-one correspondence with the set H1 of the, it's a non-abelian cohomology sheaf, the first one, so it's rather simple, of this sheaf here. The sheaf is not an abelian sheaf, but it's not very bad, it is triangular, and it is a successive central extension of vector bundles. So theory is not so complicated. So all I said is for integral slopes, including the fact that you have privileged cocycles. And now I summarize what can be done for arbitrary slopes. We can do ramification in order to make the slopes integral. And you can do the process with a ramified variable and have a big bijection, and then the one-to-one correspondence can be descended, so that you have exactly the same canonical map, even without the assumption. The difference, so to do it concretely, we have to use some degree of ramification in order to take all the denominators away, but when we are finished, it does not depend on the degree of ramification. What we do not have is the intermediate step, remember? There is something at the middle, which are privileged cocycles, which have some importance in Galois theory, and there is no equivalence here for arbitrary slopes. Okay. So I will be very swift about Galois theory. This is a paper by Jean-Pierre Ramis and myself in the Annals of École Normale Supérieure, where we completely describe what the universal Galois group of equations looks like. And in particular, it has a triangular part, a triangular subgroup called the Stokes component, which we completely describe through its Lie algebra. And from this, we solve the inverse problem for local analytic equations, but with integral slopes. Okay, so this was done a few years ago. So these last slides, are devoted to describing in detail what the universal Galois group looks like. So you just take me in faith. And then, okay, I go on the, in the end, what we get is that there is a semi-simple part in the group, semi-direct product, and the triangular part is described through its Lie algebra, and you can find another algebra, which is the completion of a sub-Lie algebra of the algebraic Lie algebra, which has exactly the same representations and that you can describe easily through free generators, which is the main tool for solving the inverse problem. Okay? So that's what we got at that time. And so what I am saying is that for arbitrary slope, also through some trick going through ramification, you can describe completely the general Galois group. The difference being that this time it's not anymore a semi-direct product, it's a central extension with a rather complicated description, but you can describe completely the representations and also probably, but this is not yet done. You have explicit Riemann-Hilbert correspondence, that is, the group represented has a part described by explicit generators. It's not pro-algebraic group, it's discrete, including its Lie part. And so probably you can, oh, sorry. So I steal you. Shut up. No, I am out of time, as you noticed. So all I say is that we can't solve the inverse problem in that case, too, but we did not yet. That's all. Right. We are tired. We are very slow. No, it's recent. Okay, but I think we can solve the inverse problem. It seems that from what we have as a description, we will not meet any more substantial difficulties. But okay, this is not honest. We have not.